So this is Unit 8, Chemical Reactions, and we're on the bottom of page 6, halfway through page 6. In this class, we are going to discuss 5 basic types of chemical reactions. So the type of chemical reaction can usually be identified by looking at the chemical equation. So when we're talking about what kind of chemical reaction, how do we classify it? We're not necessarily looking at, did a liquid turn into a solid, or, did this get hot or did this get cold? We're not looking at specifics like that. We are looking at the structure of the chemical equation. And it falls into 5 basic types. The first is what's known as a synthesis reaction. The Haber process falls into this category, synthesis. This is a reaction where we have 2 or possibly more reactants and only one product. In this reaction, we have 2 elements or compounds, and they are combining to synthesize a single larger product. Here's a note: if you have 2 elements that react, it automatically has to be a synthesis reaction. You have 2 of the smallest possible pieces. The only thing that they can do is combine and make a larger product. The Haber process is a synthesis reaction. You have nitrogen, N2, and hydrogen, H2, creating ammonia. 2 reactants, 1 larger product. As we go through these, we'll have some general equations, and these are just symbols that represent whatever they could be. For instance, in this general equation for a synthesis reaction, we have 2 reactants forming 1 larger product. Excuse me. The product automatically includes both of the reactants, and that's why you have both of these separately, and here they are combined. Now, the thing about these general equations is that I didn't put in subscripts or anything like that. If it were the Haber process, it's N2 plus H2 yields NH3. So I'm going to give you a few examples, and like I mentioned at the end of the last video, rather than giving you a bunch of balancing equation samples at once, we're going to distribute them throughout these different types of chemical reactions. So the first one that I'm going to give you is NO2 gas plus oxygen gas, and it yields N2O5. If you need to review the steps for balancing an equation, you can look at the top of this page. Step 1 is write the skeleton equation. This is step 1. Step 2 is count the atoms. So I'm counting them. So looking at nitrogen by itself, I have 1 in the reactants, I have 2 in the products. That tells me whatever happens, I'm going to have to double this one. Looking at the oxygens, I have 2 plus 2 is 4, and over here I have 5. here are some things that I notice as we go through this. And I guess let me go ahead and write this one in just so we can keep track. 1, 2, 4, 5. This is something that you'll learn to notice eventually, because most of you will jump right in and put a 2 right here, which is fine. And then you'll try to balance the oxygens, and it's going to cause some problems. This side this side has an odd number of oxygen, and this side is always even. And so the first thing I would do is make it so that we have an even number of oxygens in the products. And that means putting in a coefficient of 2. That changes the oxygens to 10, which is an even number. And it changes the nitrogens to 4. This is going to make our job a little bit easier, because now, look, I have 1 nitrogen and 4 nitrogens. Well, this is going to be fairly easy because I can put a 4 here, and now my nitrogens are fine. This also changed the number of oxygens that I have here, because I had 4, but I changed this. I now have 4 times 2 is 8, plus 2 more is 10. And it looks like we're balanced. So let's go ahead and check our work just to be sure. 4 nitrogens, 2 times 2 is 4 nitrogens. For oxygens, we have 10 in the products. Here we have 4 times 2 is 8, plus 2 more is 10, and it really is balanced. This is one where it could be a little bit challenging, and I probably made it look easier than it is. But given just a little bit of time and thinking about it, shouldn't be too difficult. So let's look at another one. In this reaction, I'm going to have hydrogen gas reacting with chlorine gas. Hydrogen gas is one of my diatomics, H2. Plus, and I'm going to leave some space here just in case I need to put a coefficient. Chlorine gas, which is Cl2. That was also one of my diatomic molecules. Hydrogen gas plus chlorine gas yields HCl. So balancing, we have hydrogen, we have chlorine. In the reactants on the left side, we have 2 hydrogens, 2 chlorines. In the products on the right side, we have 1 hydrogen, 1 chlorine. And so this one's pretty straightforward. We have twice as many atoms of everything in the reactants as in the products. And so all we have to do is add a coefficient of 2. That changes both of these. And then we just check our work. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. I'm going to give us one more, and this one's going to go back to figuring out the chemical formulas of an ionic compound. So I'm going to add in a little bit of a review challenge here. solid aluminum plus bromine, which is one of my diatomics, and this is a liquid, yields something. It's not a very common type of question in this class, but it's a possibility. The question would say, write the balanced equation of the synthesis between aluminum and bromine. And this is the information we have. So we have two elements, which means it's automatically synthesis, and they're creating one larger product, which is an ionic compound. Aluminum is a metal, bromine is a nonmetal. If you think you can do this by yourself, pause it and give it a try. Here's what's going to happen. So I know that aluminum, when it forms its ion for this compound, is going to be 3+. I know this because on the periodic table it's in group 13. That means it's 3+. Bromine, Br, it's a halogen. It's in group 17, which means it has a -1 charge. Now you're probably comparing this to this. There was one aluminum. Yeah, sure. Here there was a Br2. I don't care about the subscript right now. All I care about is the Br and its charge. That 2, that subscript needs to disappear. And so remember, we switched the charges. The 3 goes over here, and this is a 1, which goes over here. And that's the chemical formula that I end up with. When aluminum and bromine react, I end up with aluminum bromide. I would expect you to be able to get to this from these based on what I've taught you. If you don't feel like you can, you'll need to review, you'll need to get a tutor, or you need to come talk to me, possibly a combination of the 3. I'll give you one piece of information. This is a solid, and I do not expect you to remember that, but it's always customary to put in the state of matter, which is why I'm including it here. We now have our skeleton equation. This is where we can start balancing the equation because the skeleton equation was step 1. So I'm going to stick with the system that I've been showing you. Counting up my atoms. For the aluminum, there is 1 in the reactants, there is 1 in the products. So it doesn't mean it's balanced as the equation as a whole, it just means that aluminum is a terrible place to start because there's nothing to do. And then the bromine. There are 2 in the reactants, there are 3 in the products. Bromine is the one that has numbers that are not equal. That means bromine is our starting point. If you think back to the previous page when we talked about the Haber process, this is one of those types. It's a least common multiple. The easiest way to make sure that these are the same is to multiply them together. So that means, let me do it here first. We want 6 of each of these, the least common multiple. That means my coefficient here is going to be a 3. It means my coefficient here is going to be a 2. This is where a lot of students will stop and say that they are done, but they did not check their work. Here's something that happened. We changed the number of bromines in the products, which means we also changed the number of aluminums. We just didn't change it on our little scoreboard here. So we need to fix that. And in order for this to be balanced, these need to be equal, which means aluminum needs a coefficient of 2. 2 aluminums, 2 aluminums. 3 times 2 is 6 bromines. 2 times 3, 6 bromines. The next type of chemical reaction is called decomposition. In this type of a reaction, we have a single reactant breaking down into 2, possibly more, products. In this reaction, the reactant breaks down or decomposes. Those really mean the same thing here. And we're getting 2 or more smaller products. So we have one reactant and it's breaking into pieces. We're getting smaller pieces, smaller products. A reaction that we've already talked about is peroxide, hydrogen peroxide. This is something that most people keep in their bathrooms, maybe in the medicine cabinet. And the thought is, if you get a cut, you pour this on it, and it makes bubbles, and that's killing bacteria. Maybe it's killing some of the bacteria, possibly. Other bacteria are more or less immune to it. They can digest hydrogen peroxide, so you're not really hurting it. Those are the ones that we're worried about. Anyway, pour peroxide on a cut. Typically, it results in bubbles as it decomposes, and it's forming water and oxygen gas. If anything, the oxygen gas is helping. A decomposition reaction is represented by the general equation AB yields A plus B. One reactant turning into 2 smaller products. Some examples. H2CO3, which is one possible thing that you get when you dissolve carbon dioxide in water. But this compound will decompose into liquid water and carbon dioxide gas. And so we look at this equation. I want to know if it's balanced. We have a skeleton equation here. Let's go ahead and tally everything up. This is the first equation we've seen with 3 different elements. Everything works the same outside of that. Hydrogen, carbon, oxygen. In the reactants, 2 hydrogens, 1 carbon, 3 oxygens. In the products, here's 2 hydrogens, there's 1 carbon, and here's 1, 2, 3 oxygens. This one's already balanced. So it's possible that when all the coefficients are 1, it could already be balanced. Here's what it really looks like I mean, you can leave these blank. If there's a 1, it's meant to be implied, like the oxygen here. There's no subscript, but it's 1. It's one of each of these. This is another instance where we can just leave those off. If it helps you to see them, that's fine. Yeah, they are 1s, even though we don't see them. Another example, KClO4. And this is a chlorine, not a carbon and an iodine. It is a chlorine. Potassium perchlorate. This is one of the polyatomic ions that we had looked at briefly in a previous unit. So this potassium perchlorate is a solid, and what happens is it decomposes, which means it's breaking down into smaller pieces. It's turning into potassium chloride, and it's turning into oxygen gas. Write the states in here. I can tell this is a decomposition reaction by looking at the chemical equation. 1 reactant, multiple products, decomposition. So first thing I'm going to do is count up all of the atoms that I have. So there's 1 potassium, 1 chlorine, 4 oxygens. Over here, 1 potassium, 1 chlorine, and 2 oxygens. And so we look at this one, and really the only thing that is wrong with it is the oxygen. And so we need this to be 4, which means we're going to add a coefficient of 2. Another reaction. So Hg is mercury. This is mercury oxide. It's an ionic compound. It is a solid. It's sort of a powder substance. And when it is heated, it turns into liquid mercury and oxygen gas. So we need to count these up. There's only 2 things. So there's 1 of each of them. And the reactants and the products, there's 1 mercury and 2 oxygens. So if I put a 2 here, that balances the oxygens, but it changes the mercury. And to fix this, I add a 2 to the mercury, and that'll fix it. If you would like more examples, come see me or send me an email and we can talk. I have lots of examples, and we've got time for questions. The last thing to note about these two types of equations, synthesis and decomposition, is that they are the reverse of each other. So we've talked about your cell phone battery. To produce electricity to operate the phone, there's a chemical reaction occurring, and then the battery dies eventually, or it gets low at least. And then you plug it in, and the chemical reaction reverses. It goes backwards. The energy flows in the opposite direction, and instead of killing the battery, it charges the battery. If you have a synthesis reaction, for instance, this is the synthesis of water. And that's something that I might ask you because you at some point will know how to do these. If I said the synthesis of water, you would know that we're synthesizing water and making it from its smaller pieces. This is what normally happens when there's hydrogen gas and it reacts with oxygen, you get water. That's a natural thing. If you were to flip it around, you get something a little unnatural, and that is water turning into hydrogen gas and oxygen gas. It's kind of like your cell phone battery. This one, like using the battery, is pretty natural. This is just the way it works. In order to do the opposite reaction, we have to plug it in. We have to add electricity. Same idea here. If I run a large amount of electricity through some water, it will split up into these components.